Hello students, welcome back, and let's talk about problem 2. Problem 2 is about a first order linear differential equation. In general, it can be written like this. Y prime, the derivative, plus pt times y of t is equal to g of t, like this. And part A is asking you to prove this integrating factor theorem. That is, q of t is an antiderivative of this coefficient function p. Then e to the qt power is the integrating factor with this kind of property. And of course, you can use this to prove the next problem here. Okay, let's go ahead with the proof. And I can think of two different ways, and one is a forward direction. Okay, let's see. Start from this equation, and then we simply multiply e to the qt power, this one, to both left-hand side and right-hand side of the equation, which means multiply to each term. Multiply, multiply, and then multiply. What did I change to this equation? Absolutely nothing. If I multiplied by 0, then maybe something changed, but no, I didn't multiply to 0. Exponential is never 0, so this is perfectly fine. And then let's apply some, let's apply the definition, excuse me. Q is an antiderivative of this p, so this p of t here, which I'm highlighting in red, is the same as q prime by definition. Okay, now let's apply the chain rule and product rule. You see, if you look at the product rule, this is y prime derivative of the first function times the second function, and this is equivalent to first function and the derivative of the second function. Maybe I will write one extra step here. Okay, move that to the other side, and then first function and then the derivative of the second function. Please note that exponential, when taking the derivative, stay the same, and then by chain rule the derivative of the inside comes out, so we get the left hand side. Right hand side, of course, there's nothing to change. That's one type of proof, and that's the way our textbook author did. Another proof, we can do it backward. Start from the conclusion here and then apply the derivative. So from here, apply the derivative. Use the product rule. So derivative of the first function times the second function. First function times the derivative of the second function. Here, q prime, which I am highlighting in red, came from the chain rule, and in turn that is equivalent to p of t. Alright, we got it here. And divide everything by exponential, which is always possible because I'm not dividing by 0. I'm gonna get this equation. Again, let me highlight this p of t in red so that you can see where this thing came into play and compare that with the original problem. It's the same deal. Either way, it works out. Forward direction from the original problem, and then multiply by integrating factor to each term, and then apply the chain rule and especially product rule backward. Applying derivative rule backward can be a little bit tricky, so if you know the answer in already, okay, let's take the derivative in forward direction, then just apply product rule and chain rule and recognize q prime is p, then you get the original equation. Either way, it works out. Generally, students did well in this problem, and I'm satisfied with that. Next, let's go to an application problem here. Let's see. It should be of this form to apply that, so this t plus 1 has to go. Here we go. Divide it away, and we get, I may need a little bit bigger font. So divide away by t plus 1, and we get precisely the same expression as this one, the original one. So all we have to do is to multiply e to the q power, and here it is e to the q power computation, e to the antiderivative of p. So antiderivative of 1 over t plus 1, that's e to the logarithm. So we get something simple in the end. Integrating factor is t plus 1. Therefore, the final expression here in previous problem can be rewritten like this. Let's see. Yeah, let me copy and paste this thing here. That expression which we established in the previous part can be written as the e to the q power integrating factor is just t plus 1. And then multiply by that, so we get just log of t. So this is exactly the same as this one. And we can start from there. Alright, let's start from here. Take the antiderivative, and then we're going to get the left-hand side. And the right-hand side, we get the antiderivative of log of t, and this is how you take the antiderivative of logarithm. If you look up an integral table, you're going to get this formula. But if you don't remember, then you can do it through integration by parts. Or like this. I'll leave the detail to you. And alright, and let's solve for y by dividing the t plus 1 away. Here we go, we have the general solution. Okay. We're done with about 3/4 of the problem, maybe more. In this case, maybe 80%. Let's find out the final answer through the initial condition or initial value condition, IVC. Plug in t equals to 1 and y of 1 is equal to 2. Alright, plug it in. Log of 1 is 0, so we get this kind of equation. We get c is equal to 5. So it's 5, so plug it in over here, then that is the final answer. And the result for this problem was surprisingly disappointing. I'm really surprised because if you couldn't handle this first problem, okay, it's understandable if you screw up in the second problem either, but most people did okay here, did well, and didn't really know what to do here, even though, you see, this equation here is not in the standard form. You have to have the derivative y prime, so this t plus 1 has to go. Divide everything by t plus 1, and I have to have t plus 1 in denominator for both of these, this one and that one. And many students miss this one. Got this one, yeah, but missed this one. And then, of course, because of that, the computation could not be completed. I mean, this is p, so if you don't have p, then you cannot get integrating factor. You cannot get capital Q, and you cannot get e to the q power. You can't really do anything if you don't have this. So that was a bit disappointing, but in any case, that was not intended as a hard problem.